Okay, I think we're becoming pretty full now here. So let's get ready for the next talk. We have Hanna Swedenklef here, who will talk from Norrköping, who will tell us about machine learning. And this will be the final talk for this session. Yes, please take it away.
Hey, cool. So, hello everyone. Today I'm going to give a presentation about getting started with machine learning in GIS. But I will start with a bit of a disclaimer. So, machine learning is such a huge, complex field that doing a full presentation and aiming to go into loads of the technicalities and the theory and all of that is a bit ambitious for a 20-minute presentation. And I would not even claim to be the person to give that full breakdown into all the technical details and the maths and all of that. So as a little bit about me, my background is in remote sensing and GIS. And during my master's degree, I was introduced to some really cool ways to kind of level up the GIS and remote sensing analysis that I was doing with machine learning for geospatial data. And that really sparked my love and my interest in it. And so since starting at Norrköping last year, that's been a big focus of what I've been working with. So today's presentation is not at all about the theory, so sorry if that's what you were hoping for, but really all about the practical insights and kind of the problem-solving process of how can we take a geospatial problem and level up a little bit with machine learning. So hopefully this inspires you all to how you might be able to enhance the GIS workflows that you work with. So before we go into how we can apply machine learning to GIS, let's talk a little bit about what it actually is. So at its simplest, it's all about the process of teaching a computer to recognize patterns and make predictions from data without having to explicitly program it to do something based on rules. So I guess unlike some of the processing algorithms that you might use where it goes through a very predefined set of steps, with machine learning, you give the model a whole bunch of data and you tell it to identify patterns, find relationships, trends, and things like that all on its own. And so when we think about machine learning in GIS, it's really, really cool because we work with so much spatial data. And so it can be applied to things like satellite images, LiDAR point clouds, field survey results. And yeah, machine learning can help us process and make sense of these massive amounts of data. So when we think about how we might use them as GIS users, typically the tasks that we might want to do could fall into one of these three categories. And so the way I've structured this presentation is I'm going to go through each of the three categories and explain about how it might work as a bit of inspiration through an example. So we're going to start with prediction. And so prediction is all about estimating unknown values at unsampled locations. And so the problem that I'm going to explain this through is something that I worked on last year. And here we were trying to create a continuous map of air temperatures across a city because it's really helpful for urban planning, especially against things like urban heat island. But no matter what data source you use, you are not going to have a temperature measurement everywhere. We used a really, really cool data set, and these are all crowdsourced weather stations. So it's awesome. Everyone, you can buy one of these stations, put it in your garden, it uploads to the cloud, get it through an API. But still, you can see there's a lot of gaps. And so I guess with traditional GIS, what you might say is, all right, if it's 20 degrees here and 25 degrees here, maybe it's 23 in the middle. But that's not taking into account anything about the actual land cover or the geography of that location. So It was solved with machine learning by building a regression algorithm to estimate or to create a relationship between air temperature and different satellite image predictors to be able to kind of fill in the gaps where you don't have a weather station. And to show you a little bit what that might look like, or what it did look like, we first need input data into our model. So here I've given 2 screenshots from Google Earth to help illustrate it. But imagine we have a weather station at the top location and the bottom location. And we as humans can see that and see it makes sense. Of course, the top one's probably going to be warmer than the bottom one. But what is it in our minds that tells us that? There's a whole bunch of different factors that it might be. We see the top one has a lot of concrete, and we know that concrete really absorbs heat a lot more so than natural land cover. So we imagine maybe the land surface temperature in the top one is higher, and that could be why it's warmer. We look at the bottom one, and we see that it's surrounded by water. We know water has a cooling effect, so maybe that's why it's cooler. The vegetation is super different. You know, you have just a couple trees in the top one, and the bottom one is super, super dense. The building height is very, very different, but there's also so many more different spatial reasons that could explain this difference in temperature. So we do that for all of the stations we have at all of the different times we have. We collect all of these possible explainers to help train a model. And so we use a regression algorithm, and we can kind of think of the way that the model learns the patterns is by analyzing how the different predictors relate to the measured temperature. So it goes through all of the data, and you can kind of think of it like a flow chart structure like this, where it creates a set of rules for itself based on what it learns. That, okay, we see a lot of times when there's a lot of vegetation, it's a lot cooler, kind of the things that I said earlier. So then later it knows these rules, I guess, to predict temperature in areas that are unsampled, or we don't have the weather station as ground truth. So if we want to make an entire raster of air temperature across a city, we show the model new data. So if we look at 2 new fake screenshots from Google Earth, and we think about which ones might be warm and which ones might be cool, we can see that there's a lot of similar characteristics to what the model was shown before. And so the model might be able to guess, all right, the top one was quite similar to the bottom one before, it's probably also going to be cool, and vice versa. And so if you were to divide a city up into raster cells, you could do this model prediction at every single raster cell. And then over the course of a whole raster cell, you have an air temperature prediction. So that is regression. Next, I'm going to talk about the second category of application of machine learning that I wanted to talk about, and that is classification. So that is all about teaching a model to recognize and assign labels to different types of data. And so this one is super nice for those who work with imagery. I imagine many of you have experienced a similar frustration where you have to digitize the boundaries of something, whether it's forests or water or urban land or something like that from an orthophoto or a historical map or satellite imagery. But you load into the image into QGIS, you open the editing toolbar, and you click, 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 and then your fingers cramp up and you're not having a fun time. And so machine learning classification is a really good tool to speed this up, because instead of having to trace the entire study site by hand, we can focus on training the model to recognize and classify the different features directly from the imagery. So the problem I've come up with here to help explain it is, imagine if I asked you to create a shapefile of the snow extent in a very popular skiing resort here in Sweden. Of course, we know that throughout the spring, the snow melts. And if you wanted to know, for example, in May, where is the snow in Åre skiing resort, you would really, really hate me if I asked you to do that, because it would be painstaking to go through and make so many shapefiles. So I'm going to talk a little bit about the workflow for using machine learning to speed that up. So instead of digitizing the entire study site, we could focus on picking out just a few key areas. And we pick areas that we think captures the different characteristics quite well. So we pick one at the top, you see it's a lot of snow, the bottom there's no snow, and some kind of little bits in between. And we make very careful shape files of just these areas. So we could assign a field with a value of 0 to the areas that don't have snow, and then a value of 1 to the areas that do have snow. And there we have a nice label that represents kind of the truth of the situation for a machine learning model for those specific areas. Then we, similar to with the regression example that I gave, we show a machine learning model the place that we know the true value for, and it can learn what characteristics in the image correspond to snow and what characteristics correspond to not snow. So quite intuitively for us, we can see there's a strong correlation between where the image is white and where it's snow. And so the model can learn that. And then if we show it the rest of the image where we didn't draw any labels, it can compare what it learned in training to what it learned in training to what it has. And so if a pixel looks similar to the pixels that were classified as snow, it will also be classified as snow, and then vice versa. And so by this, we can really speed up the process to create a prediction across a wider area. And of course, it might not be perfect, and actually it's never really perfect. So of course, there's going to need to be a bit of adjustment there. But if you create more training data or you refine the way that you do your predictions, of course, it can perform better or worse if you don't. Then lastly, I'm going to talk about clustering. So clustering is a machine learning technique that groups data points based on similarity. And so in this approach, you don't need any labels, and the model just finds finds patterns within the data. And so it's a really cool task to use in GIS because it can help us identify spatial patterns when there's a lot of noise and we might not be able to make those visual distinctions ourselves. So it can be applied to so many different tasks, from identifying population density hotspots or creating crime hotspot zones, or in the case that I'm going to give, caffeine clusters. So the example I gave here is, imagine we're on our way back home to wherever home is, maybe via Stockholm, and we want to know what areas in the city are the most caffeinated. Maybe we need a little pick-me-up. And so here I'm going to actually go into QGIS and do a little demo about how we can use a clustering algorithm. So let's see. Here we go. So I have a script and I'll walk through what the script all does, but I'm first going to open up the attribute table of the cafes and we'll look at it. So these I just downloaded from the Google Places API. So these are the exact results that you'd get if you opened up Google Maps and searched cafe. And we have a name to the cafe, a place, a rating, so the average review, and the total number of ratings there. And I'll walk through the beginning of what the script does, and then I'll press play, and then we'll look at the outputs together. So first, we load in the layer, and we extract the points and their attributes. And the first thing that I wanted to do was delete the point if it didn't have enough reviews. I don't know if you guys have experienced similar on Google Maps where you look at something and it has like one review and you don't really know whether it actually exists or not. So we've deleted anything that is maybe not real. And then I use a clustering algorithm called dbScan. And so this is a density-based clustering algorithm. So it tries to create groups based on the distribution of data. And if there doesn't belong to a group, it's considered as noise or an outlier. So here you use two different parameters. You specify how close 2 points need to be together to be part of the same group. and then how many points you need to have a group. And then it fits the model there and creates these clusters. I'm going to play this now, and then I'm going to open this before I explain the rest of the script. So let me close this layer. And now we can see the result of it. And so I personally think it's really, really cool because it took quite noisy data. If we were to look at this kind of at the wider scale, it's a little bit hard. We can see, of course, the center has more cafes and the outsides don't. But beyond that, it's a little bit hard to really group it. And here now we have these quite distinct groups. This -1 is any noise, so we can take that out. And now we have our clusters. And it's really cool because as somebody who lives in Stockholm, you can actually really notice kind of the vibe shift between the different clusters. And I think that that's really awesome that it reflects that way in the output. But then if we want to take it a little bit further and then integrate it with the kind of normal GIS analysis that we might do, the rest of this script just creates a polygon to enclose the shape, a convex hull, and then calculates the average rating between each of them. And I just think it's a really cool way to go from the super, super messy data, no idea where the best place to get coffee in Stockholm is, through to this, where we have these individual polygons with a rating. So we can use that if anyone's in Stockholm often and wants a good place to fika. We know maybe avoid the old town tourist traps and go to this area Södermalm instead. I actually tried to do this for Norrköping. I did it first for Stockholm, then thought, no, it's more interesting for Norrköping, but it was a little bit small of a city, so it was just all one cluster. Lastly, I'm just going to go one last slide to give a little bit last on what machine learning is not. Machine learning is not magic, so you can't expect, if you have really bad data, you can't use machine learning as a saving grace to improve your outcomes because it really relies on having good quality data to perform well. Machine learning models are also not always accurate, so it's really important to take the outputs with a grain of salt because all machine learning algorithms have a certain accuracy. None are perfectly accurate, so if it looks wrong, it might actually just be wrong. And lastly, it's not one size fits all. So different tasks are going to require different algorithms and models. So it's really important to take some time to really figure out what you want to do, what data you have to figure out what is right for your task. But then I will leave it there and say thank you. Hopefully this was interesting and is sparking some creative ideas about how you might be able to get into machine learning if you haven't before. Thank you.